Hi guys, today I'm going to start some theoretical expected examples on contour integration. Very important. So let's go for it. Example 1. Prove that the integration from 0 to 2 pi sine square theta over a plus b cos theta d theta is equal to 2 pi over b square into a square minus square root of a square minus b square, where a is strictly greater than b and b is further strictly greater than 0. Now in this example, I'm having sine theta also and cos theta also, right? And let's ensure about our limits. Yes, our limits are from 0 to 2 pi. That means we are having a complete circle, right? So there is no need to change in any limits. We already need this limit from 0 to 2 pi. Alright guys, so now you just have to put the z into the polar form. So put z equal to e to the power iota theta, and from here d theta is equal to dz over iota z. Thus this integration will be equal to, alright, we know that at the very start of the contour integration, I have written some of the remarks, and there I mentioned that sine of theta is equal to 1 over 2 iota z minus 1 over z, and cos of theta is equal to 1 over 2 z plus 1 by 2. So what are we waiting for? Let's put these values in this integration. So this will be 0 to 2 pi sine square theta, which is 1 over 2 iota z minus 1 over z whole square over a plus b. This is z minus z plus 1 over z divided by 2, and this d theta is dz over iota z, where this c is a complete circle mod z equal to 1, and this is very important to note. Whenever we change this into z in terms of z, when the integration is changed, we have to erase the limits and write down here c, which denotes that c is a circle mod z is equal to 1. Very fine. So this is further equal to 1 over, this is minus 1 over 2 iota. If you solve this, you will get z to the power 4 minus 2z square plus 1 over, this is z square into bz square plus 2az plus b dz. And I'm putting this whole fraction as a function, that is f of z dz. So everything is in the form of z, so I'm writing this as a function f of z dz. Now poles of this function are given by, we have to take the denominator equal to 0. I have taken this denominator equal to 0, denominator of fz, this thing, right? And yes, z square should also come. So z square bz square plus 2az plus b is equal to 0. And from here, I get my z as 0, 0, because this is a square over here. So I'm having two zeros, and this root of this quadratic polynomial as minus a plus minus square root of a square minus b square over b. So these are nothing but your poles. And yes, because 0 is here 2 times, that means I'm having double pole. So 0 is a pole of order 2, right? And I'm taking one root as alpha, which is minus a plus square root of a square minus b square over b, and the other root as beta, that is minus a minus square root of a square minus b square over b. Now we have to check which of these poles lies inside the circle mod z is equal to 1. This is the circle mod z is equal to 1, and of course 0 0 should lie inside the circle, so this 0 pole is inside the circle and is of order 2. And let's check what is mod of alpha. Is it less than 1 or greater than 1? See, since a is greater than b and b is greater than 0, if you check mod of beta, then this sign will change into positive. Yes, mod of beta will be positive. And because this a is greater than b, then of course this mod of beta is strictly greater than 1, right? And because if you take their product, alpha beta, if you take their product and take their mod, then that will be equal to 1. You can apply the formula a plus b and a minus b, their product is equal to a square minus b square. So from there you get alpha beta, the product is equal to 1, right? And mod of beta is also strictly greater than 1. And because this mod product is equal to 1, and can I write mod alpha is equal to 1 over mod beta? Of course, yes. And because mod beta is greater than 1, then its reciprocal will be less than 1. And from here, I get mod alpha to be strictly less than 1, which means if mod of beta is greater than 1, that means beta lies outside the circle. And mod alpha is strictly less than 1, that means alpha lies inside the circle. So the poles of the Fz which are lying inside the circles are 0, 0 and alpha. 0 is of order 2 plus one simple pole alpha, right? So now I am going to calculate the residue of the function at 0, which is the pole of order 2, and whenever we are having the pole of order k, then their formula is to find the residue of Fz at any point having order k, then that formula is 1 over k minus 1 factorial, limit z tends to 0, 0 is a point where you are having your pole, and we have to derivate z minus 0 whole square y square because 0 is of order 2. And if it is a simple pole, then I cannot write here 2. The formula is other one. So because here k is 2, so I have written here 2 multiply by f of z. Whatever pole you are having, you have to write that power. Okay. So because it is the pole of order 2, so k is 2 here. So put the value 2 minus 1 factorial is 1 factorial, that is equal to 1 only. So limit z tends to 0. D by dz of, we have to derivate. Now here 2 minus 1 is 1, that means we have to derivate only one time. Z minus 0 whole square is z square into the function fz, and that is equal to see here your function is, yes, 1 over 2 iota z the power 4 minus 2z square plus 1 over this denominator, right? Is there any leading coefficient? Yes, b is a leading coefficient. We have to take this b outside and write z minus alpha into z minus beta, right? And rest is same. We just put this quadratic polynomial into the factors. So this is minus 1 over 2 iota z square, z the power 4, z minus 0 is z, so this is z square, z the power 4 minus 2z square plus 1 over the denominator, that is z square bz square plus 2az plus b. This z square is cancelled out with this z square. This is equal to limit z tends to 0 minus 1 over 2 iota d by dz of, okay, you have to find the derivative of this function with respect to z, right? And when you find the derivative of this function, you will get z minus 2a over b square. And because can I write, if I multiply and divide by iota, so this iota square is minus 1, this iota square and this negative sign cancelled out, so I am having this as limit z tends to 0 iota over 2 z minus 2a over b square. Now limit z tends to 0, put z equal to 0 over here, I get iota by 2 minus 2a over b square. So this is equal to 2 cancel, this is minus a iota over b square, right? Now I am taking the residue of fz at alpha. So for that, because alpha is a simple pole, so the formula is limit z tends to alpha, z minus alpha into f of z. Now I am putting this function, the denominator of this function in terms of the factors, so that z minus alpha cancelled out. So this is minus 1 over 2 iota limit z tends to alpha, z minus alpha. Now f of z is z the power 4 minus 2z square plus 1 over z square bz square plus 2az plus b. So this is minus 1 over 2 iota limit z tends to alpha, z minus alpha, z the power 4 minus 2z square plus 1 divide by z square. Now take this leading coefficient outside and write the quadratic polynomial into the factors, that is z minus alpha into z minus beta, because alpha and beta are the roots of this quadratic polynomial. So this is equal to minus 1 over 2 iota, this z minus alpha is cancelled out with this z minus alpha, and I am lefting up with limit z tends to alpha, z the power 4 minus 2z square plus 1 over z square b. Okay, next minus 1 over 2 iota. Before putting the value for z, I'm going to make this as this numerator into the perfect square, which is z square minus 1 over weight, z minus 1 over z whole square. First, you cancel the z square, take the z square common, and you will be lefting up with z square minus 2 plus 1 over z square, right? That is your perfect square, this. And the common that you have taken z square, that is cancelled out with this z square. So I am lefting up with this. Is it clear? Okay, I will write the step for you. I have taken z square outside, and this is z square minus 2 plus 1 over z square. and in the denominator I am having z square b. This is cancelled out, and this numerator is a perfect square, that is z minus 1 over z whole square divided by b. Is it fine? Alright. Now put the value for z tends to alpha. Minus 1 over 2 iota. This is alpha minus 1 over alpha whole square over b. This is alright. Z minus beta is also there. I'm very sorry. Alpha minus beta. This is equal to minus 1 over 2bi, iota, and this is, if you solve this, you will get it as alpha minus beta whole square over alpha minus beta. As alpha beta is equal to 1. If you open this, you will solve this, you solve this and apply alpha beta is equal to 1, you will get this. Now take the difference of the roots, right? And when you solve the difference of the roots, you will get the answer as iota square root of a square minus b square over b square. So I am having the residue of fz at z equal to alpha as this. Now taking the sum of the residues of fz at the points inside the circle for the point alpha plus for the point 0 of order 2. So I am having sum of the residue as, for 0 I got the residue minus ai over b square plus the residue for z equal to alpha, just now we have calculated, and that is equal to iota square root of a square minus b square over b square. And then when you solve this, you get a square minus b square minus a iota over b square. So thus, by the Cauchy residue theorem, this integration, the given integration is equal to, which is equal to integral sine over c fz dz, that is equal to 2 pi iota times the sum of the residues of fz of the points inside the circle. And we have just now calculated this sum as square root of a square minus b square minus a over b square into I. And finally this is equal to 2 pi over b square a minus square root of a square minus b square. Here ends up the solution. Next, prove that integral sine from 0 to pi a over a square plus sine square theta d theta is equal to pi over square root of 1 plus a square. 3 steps are required to get our best integration. Alright, see, this limit is from 0 to pi. Fine. First thing, we need to change it to 0 to 2 pi. Secondly, I am having sine square theta in the integration. So I need to change the sine square theta in terms of cos theta. And then we have to put the whatever angle we are having, we have to put that angle in the easier way. We have to take one another variable for that angle. Let's start. Let's first change the sine square theta into cos, so that our rule will be satisfied, that is f of 2a minus theta should be equal to f of theta, and then we are going to change the limits. So we know that 2 sin square theta is 1 minus cos 2 theta, right? So I need 2 here. Can I divide and multiply by 2 to the numerator and the denominator? Alright, so I'm going to multiply 2 with the numerator, and also I'm multiplying 2 with the denominator, so that I get 2a over 2a square plus 2 sin square theta d theta. And now I will put 2 sin square theta as 1 minus cos 2 theta over here. So this is 2a over 2a square plus 1 minus cos 2 theta d theta. Perfect. Now I can change the limit because now I have cos in this integration. Easily change your limits. Whenever I am having from 0 to pi in the limits, so I have to take this as 0 to 2 pi by dividing by 2 or multiplying by 2. Of course, by dividing by 2. And this is 2a over 2a square plus 1 minus cos of 2 theta d theta. Is it clear? Alright. Let's cancel this 2 with this 2. And also because I need a single variable over here. So instead of 2 theta, I put this 2 theta is equal to phi, and this 2 d theta is equal to d phi. So this is 0 to 2 pi a over 2a square plus 1 minus cos of phi d phi. Fine? Alright. Next, now I need to put, I'm having the limits from 0 to 2 pi. Yes. I'm having the expression in single cos phi. Yes. Now I'm going to change this in terms of z. I'm putting z into the polar form, z equal to e the power iota phi, and where d phi is dz over iota z. So this, instead of limits, I'm writing c because I got a complete circle. So this is equal to a over 2a square plus 1 minus cos phi will be changed into, yes, 1 over 2 z plus 1 by z into dz over iota z. Okay, next, take this whole of this function as f of z, where your f of z is equal to 2a iota over z square minus 4a square plus 2 into z plus 1. If you solve this denominator, you will get fz to be as this. Fine? Now, poles of fz are given by taking the denominator equal to 0, and then this is your quadratic equation, and from here I get the roots as z is equal to 2a square plus 1 plus minus 2a square root of a square plus 1. So take one of the root as alpha, 2a square plus 1 plus 2a square root of a square plus 1, and another root be as beta, 2a square plus 1 minus 2a square root of a square plus 1. Now let's check which of the root lies inside the circle. Since alpha is positive, therefore mod of alpha is greater than 1. Yes. And because alpha beta their product, and by taking the mod, this is equal to 1, and mod of alpha is greater than 1, then of course mod of beta will be strictly less than 1. If one of the root is greater than 1, then the other root will be definitely less than the opposite of the sign, right? So mod of beta is less than 1. So which of the root lies inside the circle? Yes, beta lies inside the circle and alpha lies outside the circle. Oh, now it's turn for beta. Very good. Hence, the only pole of fz inside C is at z equal to beta, which is a simple pole. So the residue of fz at beta is equal to limit z tends to beta, z minus beta into f of z. So this is equal to 2a iota. I am putting the value of fz over here. Limit z tends to beta, z minus beta over. See, your fz is this. Is there any leading coefficient? No, here leading coefficient is 1 only, right? So 2a iota I have written here, 2a iota, limit z tends to beta, z minus beta, and instead of fz, in simply this is your quadratic polynomial. There is no leading coefficient, so I just put this into factors as z minus alpha into z minus beta, simple. These are the two factors for this polynomial, so I am putting here z minus beta into z minus alpha. This you have to do, right? So these two are cancelled out. 2a iota, putting the limit 1 over beta minus alpha. Now when you solve this, take the difference of the roots. This is minus 4a square root of a square plus 1. Right, and finally this is equal to minus iota over 2 square root of a square plus 1. Right, now can I apply Cauchy residue theorem? Yes. Hence, by Cauchy's residue theorem, the given integration is equal to integral sine fz dz, which is equal to 2 pi iota times the residue of fz at the point which is lying inside the circle, and beta is lying inside the circle. We have also calculated the residue for that pole, and that residue is equal to, this is 2 pi iota into minus iota over 2 square root of a square plus 1. So this is equal to pi over, this 2 cancel, iota is minus 1. So this is a square plus 1. Fine, complete the solution. Alright, just go through the steps again and again. Do these exercises by on your own, and then you will understand the steps. More important is to solve this quadratic polynomial, to keep this polynomial in terms of factors. This is very important. So this you have to learn, and you also have to check which of the poles lies inside the circle. This is also important, and most important is the limits. What limits you are having in the exercise. If it is 0 to 2 pi, then it's okay. If not, you have to change this limit to 0 to 2 pi, right? Adjust your functions which is given in the integration. You must have cos, right? And then after changing the limits, putting the integration in terms of cos, just apply z into the polar form, put the whole function in terms of z, calculate your poles, apply the Cauchy residue theorem, and that's it. Alright. So guys, let's meet in the next video, and we are going to do some more questions on this contour integration. Actually, the whole topic is based on the exercises only, right? Okay, thank you guys. Have a very blessed and nice day. God bless you.